Hello, it's Keith here, and this is the first in the 2021 series of Z80 programming tutorials. This is a new series which starts from the absolute beginnings of Z80 assembly programming. Well, who am I? Well, I'm the author of Learn Multi-Platform Assembly with Chibi-Akumas, the book on Amazon, and I also wrote the Chibi-Akumas games. There was Chibi-Akumas 1, which came out for the Amstrad CPC, ZX Spectrum, Enterprise, and MSX2, and there was Chibi-Akumas Episode 2 on the CPC, and I've also done a variety of other little games, Photon, Y-Quest, Suck Hunt, on various different systems, not just the Z80. I've been branching out into more and more assembly language systems. This tutorial covers the Z80. This is an updated version of my original series, which was very popular, but that series was done many years ago when I was new to YouTube. My setup wasn't as good as it is now, and hopefully I'm better at making videos now. And also I've changed the way that I program my tutorials. The original series used the WinApe assembler and emulator. This series does not. This purely uses VASM, and it will work on a variety of different systems. So if you're not interested in the Amstrad CPC or you can't use WinApe, you should still be able to watch these tutorials and use them on your own system. And that's the important part. You can download the build scripts, the development tools, the assemblers, everything for your Windows-based system, and you can run the examples hopefully with virtually no work of your own. Just install them and get them started. So I'm hoping to get started with programming as quickly as possible, and hopefully you'll be able to use these tutorials on your own machine. Now, all of the tutorials come in 3 parts: the video you're watching now, the source code you can download and run yourself, and also the web-based content, which you can see here. So every single lesson has the same content as the video in text. So if you don't want to watch the videos at all, you can just go to the website and you can read them, and you can try them out on your own machine. So whatever you want to do. As I said, I do have a book available now on Amazon, either in print or Kindle. You can buy that if you want, but there is no need for you to do so. This tutorial series is totally self-independent. Some of the content has been taken from the book because hopefully the book is the best I can explain things, but you don't need the book to help you follow this series. One thing I would recommend that you do, though, is you go to my website and you download the cheat sheet. If you see here, we've got this link here. This Cheat for Victory link is a cheat sheet, and this is a cheat sheet you can print out on your own printer, maybe A4 if you've got good eyes, or A3 if you prefer. But this is a very detailed list of all of the instructions with a description of them, and also the technical details. These won't make a lot of sense to you at the start, but when you get into programming, you're going to find this very helpful. Of course, it's free, so just go ahead and download it. I'd strongly recommend it. Now, as I say, you can download my development tools and my build scripts and get started. Enough talk, let's actually see some code running, because I know some of you want to see code very quickly, so let's get started. So these are the scripts. These have a lot of additional tools which I've written to do basic tasks like drawing text to the screen, and we're not going to cover those at this stage. I've got other tutorials that cover all of that. If you just want Hello World and you just want to see how to compile Hello World, please search my YouTube channel. I've got that for every system you can probably imagine. Okay, so this is our first example, subs and labels. And if we just run this, if I select from my list here, let's try a system. Let's try the Sega Master System here, SMS. And if I just run this here, selecting VASM SMS and OK. Well, you can see here, if I just reorganize my windows here. So here we've got a Hello World message on our screen here. Hello World, and that is our test. The clever thing is, now we just press F6 here to get this menu up, but if I select a different system like MSX1 here, if I select MSX1 and I run again, well, we've got the same Hello World 323 message. You see there's a lot of code behind the scenes that is doing the same task on a lot of different systems, and that's how this is a multi-platform series, and this should help you. If you're not interested in the CPC, that old series wasn't so good for you, but this system, this way of doing things should work on the vast majority of the systems I've covered in my tutorials. Now, there will be some limitations. Some of the systems may have memory at specific positions, and some of these tutorials write to specific memory locations in their testing, but generally speaking, these should work on any system, and we'll be trying these on a variety as we go through. So let's just fire this Hello World example up on the ZX Spectrum here. Let's just fire this up and let's see what happens. So here is our Hello World message here. So first of all, what we've got here is a jump. JP is a jump, and subs and labels is a label in our code, and you can see this label just here, subs and labels. Now the colon at the end of this doesn't specify that it's a label. It's the fact that it's at the far left of the screen that marks it as a label. You can see this is indented with a tab, this command call. That means it's not a label. If I put it at the far left, the assembler might actually mistake it for a label. I'm using Vasm. Vasm would mistake it for a label. It does depend a little bit on your assembler, but as I say, you need to, generally speaking, make sure your labels are at the far left and you put a tab indent or a series of spaces for your program code. Now, the other kind of code that we do want to discuss is comments. On the Vasm assembler, these start with a semicolon. So you can see this is a comment here. You can also see this is a comment here, and I've done my best to code comment the code to show what's going on. So we've got our label here, show hello. We've got another label. If we have a look here, we've got this message here. If I just do a search for this message here, you can see here is our message here, and we've got a string of text here and a 255 byte there. We'll go into all of this later, so don't worry. I'm going through it a little bit fast because I just wanted to discuss the concept of a label and how we can use that label, subs and labels, in our code in the form of, after this call command. Call is basically like a go sub. It goes to a label and it returns. Here we've got a load command. LD stands for load. We're loading a 16-bit register pair, HL. We'll cover this again in a moment, but we're loading that with the address of message. So message is a label, and that's being converted by our assembler to an address. We're then calling the print string routine. Now, at the end of a subroutine, because we used a call here, so this is like our go sub in BASIC. This is a subroutine, and at the end of that we have a ret command, which is return. So once our hello subroutine gets to the ret command, the execution will continue with the thing after the call to the subroutine. So in this case, the jump, JP has jumped to the finish. Okay, so all you need to take away from that is, if it starts with a semicolon, it's a comment. If it's at the far left, then it's a label. If we use that label in our code, the assembler will convert that for us. And if we're indented, it's not a label, it's a piece of code. Everything else there, now I've gone through it quickly, but we're going to go over it in later lessons and later examples anyway. So that's all you needed to have understood at this point. Now let's take a look at our second example, register loads. So we have these things known as registers. Well, what are they? Well, if we just go over to our projection screen here, you can see an image of how I imagine registers and RAM to work. So if you imagine this is our CPU here, so this is our processor, and it's the main brain of our computer, if you will. The processor talks to the RAM, which is our storage. So our RAM is separate to our processor, and there's some distance physically between the two because there's little wires between the two, and that means that writing to the RAM is not as fast as it could be. However, the CPU has a very, very small amount of RAM of its own. Now this is much, much less than the RAM. In our theoretical imaginary processor here, we've got 64 kilobytes of RAM and 16 bytes of registers. The registers, though, are very fast. Now, the way you want to think of this is basically your registers are your working memory for when you're calculating things, and when you've calculated a result, you want to store it back to RAM because we've got lots of RAM and very little registers. So that's how the registers work. Now, from the point of view of our code, at this point, we're just going to be loading data into registers as an example. So we've got a load command here, LD stands for load. And we've got a register A and a value and 69, which means hexadecimal 69. Now on the Z80, the source in a command is on the right and the destination is on the left. So we could imagine this is load A with value hexadecimal 69, or load hexadecimal 69 into register A. Now A is a special register. It's known as the accumulator, and it's in a lot of ways the most powerful register, certainly of the 8-bit registers. So let's have a look at this example running on the ZX Spectrum. Let's have a look at it. So here's our ZX Spectrum here, and if we just hit enter here, our program will start. And let's have a look at what has actually happened there. So we've told the processor to load the value and 69, hexadecimal 69, into the accumulator. And we've then run this routine called show a HLBC, which is a routine I wrote which will do the work of showing the contents of the primary registers to the screen. And if we look here at the top line, A has been loaded with the value 69, and these are all shown in hexadecimal. So that 69 there is the result of this command here, and we can confirm that, and this is where I do suggest you download the examples and try them out. If I change this to a 66 and I run again, well, now you can see that accumulator has changed to a 66. So it does seem to be that our code is changing the results on the screen. It is, of course, so I'll just say we can prove that for ourselves. Okay, so I mentioned that this is hexadecimal. What is this hexadecimal thing? Because it's possible you may not have heard of that before. Let's have a look at the screen here. So this is a screenshot of some examples of conversions from decimal to hexadecimal and binary, also octal and ASCII, which you don't need to worry about at this point. But basically, a single 8-bit register can store values from 0 to 255. And we've got values just up to 63 here, just for space. But the value 0 in decimal, and decimal is of course what we're used to, values that go from 1 to 100 or 1 to 10. These can be represented in other ways. Hexadecimal and binary are the ones we're going to be wanting to look at. So 0 in decimal is 0 in hexadecimal, and it's also 0 in binary. But things start to get a little bit strange when we go higher up. You can see binary only uses 1s and 0s. Hexadecimal and decimal look the same at first, but as soon as we get to 10, things get a little bit weird. And the reason for this is that decimal is base 10. So every time we go from 0 to 9, we then wrap up into a second digit, but hexadecimal is base 16. So this continues to the equivalent value of 15, and then the value 16 rolls into a second digit. Whereas binary, actually this is base 2, so every change goes into a second digit. Now these might seem a little bit confusing to you. I totally understand why that would be the case. Now one thing I can suggest to you is if you load up the Windows calculator and you change it to programmer mode, the Windows calculator does show all of the different representations you're likely to need. So if we type in our value of 16 here and we have the decimal option selected, you can see that is 10 in hexadecimal, 20 in octal, you probably won't need octal, and it's 1 quadruple 0 in binary. So that is how that works. Now, let's just discuss a little bit more what this is all about and why this is the case, because it is very important. Let's go over to the blackboard and let's have a look at this in more detail. As I say, decimal works in base 10 because we have 10 fingers. Well, what would happen if we had just 2 fingers, or if we had 16? How would we represent numbers there? And the reason this all came about is because electronics on computers, at least originally, weren't very reliable, and so they had to simplify things down into a way that couldn't be misrepresented. There were early analog computers, and they would represent numbers in a range from 0 to 1, and literally analog, and so floating point. But this could cause interference could cause numbers to change. So they went for a very simple alternative, which was just on or off. So if you could imagine this is our 0 volts and you could imagine this is our 5 volts. So on and off would represent 2 states, and so these could be considered to be 1 or a 0. And that's what they did, and that's where binary comes from. So everything is only on or off. Now, if we can only have ons or offs to represent our numbers, well, let's just imagine we've got 2 zeros here. This is 2 binary states that can be only on or off, and this will represent our number 0. Well, what about when we want to represent the number 1? Well, we turn one of those on, so we would have a 0 and a 1. Now, this can only go up to 1, so when we add 1 again and we go to 2, this we will then flip back to a 0, and this will become a 1, and then the number 3, both of these will be 1, and the number 4 we can't represent with 2 bits because we've used every possible combination of a 1 and a 0 in these 2 bits here. And the thing you need to think about is each of these places kind of has a value. This sort of has a value of 1, and this kind of has a value of 2 here, because this here is a value of 1, so our total is 1. This is a value of 2 here, so our total is 2. And this one, where both are set, 2 plus 1 equals 3. And if we had an extra bit here, this would be a value of 4 here. So each bit's value is twice what the previous one is in binary. Now, this is all very well and good, but the problem with binary is it's very hard to actually get to a value that would represent what we're used to in base 10. So if we have a look at my calculator routine here, and we just put in a value of 1 here in binary, this would be the maximum value of a single bit of data, and this is of course a value of 1 in decimal. You can see that just here. Well, what about if we add another 1? Well, now our value is 3. We add another 1, 7, 15, 31, 63, 127, 255. We never got to 99 or 100 or anything like that. We didn't reach any of those kind of values, and that means that binary doesn't really map to decimal in a very logical way. But let's just do that again, and let's have a look at hexadecimal. Hexadecimal is base 16, and so this is effectively a combination of 4 bits. So this will go from 1 to 3 to 7, F, 1F, 3F, 7F, FF. Now base 16 hexadecimal is basically adding some extra digits to the alphabet, so to speak. So rather than going 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, we have a letter 10A, a letter 11B, a letter 12C, a letter 13D, a letter 14E, and a letter 15F. And then when we go over 15, we roll back to 1, 0, 16. And if you look at the bit combination, you will see that the 4 bits on the left of that binary number there define the top digit, and the bottom 4 bits define the bottom digit, and 4 bits is referred to as a nibble, which is a joke because 8 bits is called a byte and half a byte is called a nibble. Ha ha, very funny. So that's how hexadecimal and binary and decimal map together. Now, if you don't understand them, you don't need to worry. As I say, use the Windows calculator to help you out. Really, all you need to understand at this point is the limit of a byte. A byte, being 8 bits, has a limit of 255. Now, actually, if we add 16 bits, so here is 16 bits, this is a value of 65535, and that's 4 Fs. These are all unsigned numbers. Signed numbers are a little bit different, but as I say, this is just something you need to roughly understand at this stage to know why you can't load a value of 3000 into a single 8-bit register, for example, a single byte register. So that is the way that decimal, hexadecimal and binary all map together, at least very quickly. You will start to understand these naturally as you do more programming. You will become familiar with them, and so if you don't understand them completely at this stage, that's totally understandable. You just need to have an understanding that there are different ways of representing numbers. We can specify a hexadecimal value with an and symbol or a dollar symbol on some machines. It does vary. Some assemblers use dollar, some use 0x, so you do need to check if you're using a different assembler to the one I am. Now here we've loaded a hexadecimal number, and the reason we did that is it's easiest to show on the screen in our monitor to see the contents of the registers, but we don't need to. We can work in decimal just fine. So here we've specified a decimal number. You'll notice there's no and symbol this time. Here we specified an and symbol, here we haven't, and so without the and symbol it's decimal. We can also specify binary with a percent symbol, and so we've got a variety of options here. And the other thing you'll notice that's interesting is the accumulator there at the first is a negative number, and this is where another tricky thing comes in. So let's just fire this up and let's see how those numbers appear on our computer. So we've loaded our accumulator with a value of -1. We've loaded our B register with a value of 69. We've loaded our C register with a decimal value of 1110000. And we've loaded our D register with a value of 255. Well, let's see how those have come out. Well, our -1 has quite curiously come out as an FF. We'll have a look at that in a moment. our value of 69 in decimal has come out as a value of 45. Well, is that correct? Well, let's try that out. If we go here and we type in a value of 69 here, you can see that the 69 in decimal is 45 in hexadecimal. So that looks like that has worked correctly. So that 45 is what we'd expect to see there. We've loaded our C register with 11110000. Now, as I say, 4 bits like this is a nibble. And so when we do this, this is effectively setting one of the letters of our hexadecimal value. And you can see that the C part here after the 45 is F0, and the F is the 4 ones, and the 0 is the 4 zeros. So that's how our binary has been converted to hexadecimal, and that's why hexadecimal is very handy when you're working with binary. And then finally we've loaded D with 255. Well, why have we loaded 255? Well, it was to make a point. We've loaded D with 255 and we've loaded our accumulator with -1, but they've both come out as 255. Very interesting. Well, before we discuss that particular conundrum, let's discuss our registers. You can see we've got A, B, C and D as destinations here. Now these are all 8-bit registers. Well, what registers do we actually have at our disposal? Well, the answer on the Z80 is a surprisingly large number. Now let's just go over here and have a look at some of them. So, well, registers on the Z80 basically come in two kinds. We have the basic Z80 8-bit registers, and a lot of the registers can be combined together into a 16-bit pair. The Z80 is only an 8-bit processor, but pairs of registers can be used for some 16-bit mathematics. So the accumulator A is our main register, and this is our workhorse. It does all of the mathematical work for us. The F register is known as the flags. This is used for various conditions and things. We'll see that later. HL, which is a 16-bit pair made up of a H register and an L register. This is the high-low pair, and this is sort of like a 16-bit accumulator in a lot of cases. It's also used as a source and a destination in memory. We'll see that in later lessons. BC is a pair made up of 8-bit B and C, and this often stands for byte count. BC can be imagined as byte count. DE is a pair as well. This can be imagined as destination. It's used in some cases as a destination. So two 8-bit registers as a 16-bit pair. We then have some special ones, IX and IY. These are indexes. These are 16-bit. They can be split up, but they're slower for that purpose, so we don't tend to use them. The other thing you need to note is that these are often used by different systems. The ZX Spectrum, for example, will get very angry if you use the IY register, and it will be prone to crash. So we won't be using that so much. We'll focus on the other ones that are more mainstream, shall we say. We've got PC. This is the program counter. We can't use this directly. It's always 16 bits. And this is the thing in the processor that points to the current running code. So it's an internal register, if you will. SP is the stack pointer, another very special register. We will discuss that in a later lesson. The R refresh register, you shouldn't use that at all. And the I register, very special interrupt vector register. You can use it, but it's not very useful. So those are all the registers available to us. Again, we're going to come across these so many times that even if you don't understand them at this stage, just don't worry about it. But I needed to discuss their existence just to make sure I was covering everything in completeness. Now, as I said before, we loaded that register A with -1 and it came to FF, and we loaded D with 255 and it came to FF. Well, why is this? Well, this is something that's a bit of a quirk of the way that the processor works with its registers. Well, why is that? Well, let's go over to the blackboard and have a look at this in more detail. Now, our registers are 8-bit, at least at this stage, and this means they can have a value of 0 to 255, because that's the limit of what can be represented within 8 bits. Now, if we've got a register that contains a value, say 254, and we add 1, it will logically go up to 255. Well, what happens if we add 1 again? Well, it physically can't store any more than 255. Our processor is not going to crash, so it's going to roll back around to 0. Very interesting. So what happens if we add 1 again? Well, of course, then it's going to go up to 1. What happens if we subtract 1? Well, it's going to go back to 0. What happens if we subtract 1 again? Well, it's going to go to 255. So whenever we go above or below the limits of our registers, we end up wrapping around back to the original limit. And this creates quite an interesting byproduct. You see, if we've got a value, say the value of 10, and we add 255, well, what happens? Well, this will cause a wraparound. This will push 10 up over 255, back to 0, and then it will continue, and we will end up back at 9. Well, that's surprising, but it means that 255 is effectively minus 1. So if we add 255 to our 10, we will end up with 9, which is what would have happened if we'd have added minus 1. And this is how the negative mathematics works in our processor. And it also means that our 8-bit value can either be considered to be 0 to 255 if it's unsigned, or alternatively minus 128 to plus 127 if it's signed. Now, I know this sounds very strange. It confused the bejeepers out of me originally. You can just take it from me that it's true at the moment. You will start to see it more later on. As I say, you can always use your Windows calculators to check this kind of thing. But it's just important to accept, if you will, that that's the case at this stage, and also to understand that there is no way that the processor needs to be told whether a register contains a very high unsigned number of 255 or a negative number of minus 1 when it comes to addition or subtraction, because the result is the same either way. And it's really the case of how our program deals with these values, whether a number is signed or unsigned. If we're going to cause our register to overflow with an addition and it's supposed to be an unsigned register, we need to check for that and actually compensate for the overflow, whereas if it's a negative number, then we don't, because that's what we intended to happen. So we'll be looking at negative numbers again later on. So don't worry again if you don't understand it at this stage. I'm going through a lot very quickly. As always, go to the website, download the source code, try it out yourself, change things, see what happens. And also, as I say, play with that Windows calculator and try and see the results for yourself and try and understand for yourself why they're true. Okay, so we've looked at some 8-bit register loads here, and as always in all of these cases, the destination was on the left, the register letter, and the source was on the right, and we've got a variety of values from 0 to 255, and minus 1 of course is a valid 8-bit value. And these were all 8-bit loads. Now what we're going to do is we're going to try some 16-bit loads with pairs of registers. So B is just 8 bits, but B and C is a 16-bit pair. So we can load this with the 16-bit value. Here we've loaded hexadecimal 1, 2, 3, 4. Then we've loaded DE with 5, 6, 7, 8. And then we've loaded HL with 1, 6, 3, 8, 3. All of these are valid 16-bit numbers. And let's see these in action. Okay, so we've loaded our BC with 1, 2, 3, 4. And you can see BC has loaded with 1, 2, 3, 4 here. We then loaded DE with 5, 6, 7, 8. And you can see DE has loaded with 5, 6, 7, 8. And then finally, we loaded HL with the value 16383, and HL has been loaded with 3FFF. Well, is that correct? Well, let's check it out. If we just put in here 16383, you can see here 16383 is 3FFF in hexadecimal. So it looks like we've done our maths okay there. Okay, so again, we've loaded our 16-bit values here in the same format. We've got the source on the right, which is what's known as an immediate value, a fixed number value, and our destination on the left, which is a register pair. Now, one thing I do need to point out to you at this stage is that we can't use any combination of registers. BC is a 16-bit pair. We can't just mix and match these as we would like. So we can't use B and E. We can only use B and C or D and E. We can't use D and C or D and B or D and D. Of course, these won't work. We have to use the matching pairs of registers. And if you download that cheat sheet I mentioned, you'll be able to see which commands are valid and aren't. So if you get confused with that kind of thing, that will help you out. So all of these are working with fixed numeric values. But of course, we aren't just limited to those, and the load command LD is capable of doing other things. And this time we're going to be looking at transferring 8-bit values from registers to registers. Okay, so what have we done here? Well, what we've done here is we've loaded the accumulator with the B register, then we've loaded the C register with the D register, then we've loaded the H register with the D register and the L register with the E register. Again, source on the right, destination on the left. So here we've loaded the accumulator with the B register. Let's see what happened. Well, you can see that the B register was 1, 2, and now the A register is also 1, 2. Here we loaded the C register with the D register. Well, now you can see that the C register is 5, 6, and the D register was 5, 6. And then we loaded the H register with the D register and the L register with the E register. So we've loaded HL with the value that was previously in DE. And this is a limitation of the Z80 instruction set. Basically, these inter-register loads, where we load a register with the value from another register, only can work at 8-bit. So we can't do HL, DE. This is not a valid command. There are some commands that will work with 16-bit values like add and subtract, but we can't load a 16-bit pair from another 16-bit pair in one go, but we can use 2 commands to do that for us. So there we go. So those are the basic register loads that we're going to start off with. Now, what we're going to do next is have a look at some memory writing. All of the examples we just looked at were working with what's known as immediate values, the fixed number values that never change. Of course, this is going to make writing a game or anything pretty hard because the numbers never change. We're going to want numbers that change, and we're also going to want to change numbers to do things. So that's what we're going to look at this time, and just for a change, we're going to try this on the Amstrad CPC. So let's just fire up our CPC emulator here, and let's get some CPC action. Now this example, because it's working with memory, will work on some of the systems, but it won't work on others. And the reason for that is that some of the systems don't have memory at the same position as we've got our example program to work with here. It should work on the master system. It should also work on the ZX Spectrum, but as I say, some of them will have ROM there or might have other things that are in the way. So we're going to try this here, and we've got a function here called monitor memdump direct, which is going to dump a memory address, in this case C000, and a number of bytes, in this case 16. So we're just using this. You don't need to worry about how it works or how to use it. It's just showing the contents of some memory to the screen. Now at the start of our program, this area of memory is entirely blank, so it's all full of zeros. And we're then going, well, what are we doing here? Well, the first thing we're doing here is we're loading the register pair HL with the 16-bit immediate value C000. And then what we're doing is we're loading the DE register with the value at address C000. Now you'll notice the first line there has just C000, and the second line has that in brackets. And by putting it in brackets, we're telling the assembler to load from the address C000, not the value C000. So that's loading DE from that address there. Now at the start, that address contains 0. So we've loaded the value 0, quite boring there. But you can see our HL has loaded with the immediate value C000 as we told it to. Okay, so we can read 16-bit values by specifying the address in brackets like this. Well, what if we want to write them? Well, we basically do the same thing. This time we've loaded the accumulator with the immediate value hexadecimal 69. The next line specifies a load where the source on the right hand side is the accumulator and the destination on the left hand side, because it's in brackets, is a memory address. So we're loading the memory address C000 with the value in the accumulator here. Okay, let's see what happened. Well, the next time we dump our memory here, you can see the accumulator is 69 and the memory address C000, that first byte there, has indeed been loaded with 69. And that's because of our command pair here. That's what we've done. So here we've written those bytes to that memory address. Now, of course, we can use any address we want as the source. Here we're using the destination registers BC and the memory address C002 as the source. And so, again, we will have loaded a 00 here in that case. What we've then done is we've loaded DE with the value 0666, and we've loaded the memory address C004 with that value in DE. Right, well, how has that come out? Well, we've got DE with 0666 here, but when we look at our memory, it's been kind of converted. It's actually 6606, which is kind of backwards. Those 2 bytes are backwards because we wanted to load 0666, but it's ended up as 6606. Well, why has that happened? Well, let's go over to our other screen over here and we'll have a look at this. This is something known as little endian. There are two ways of representing numbers over 8 bits in computing. There's big endian and there's little endian, and the vast majority of processors you're likely to come across these days are going to be little endian. This is effectively where we have what we just saw, and the numbers are effectively reversed. So if we were to store the theoretical value A, B, C and D on a big endian system, which is not the way our processor works on the Z80, the first address would store the high part, AB, the big part, and the small part, CD, would be stored in the second address. But little endian works the other way. Little endian stores the low part in the first byte and the high part in the second byte. Now, you could argue which one of these is better, but it really doesn't matter. The point is our processor works in little endian. So when we store a pair of bytes, the low byte will be stored in the first address and the high byte will be stored in the address afterwards. And quite curiously, I believe this is actually a reference to Gulliver's Travels, the book. There was two fictional tribes of people who were arguing. One ate an egg from the big end and the other ate the egg from the little end. And that's apparently where this term comes from. But as I say, we're a little endian system, and you just need to bear that in mind when you're reading and writing data and seeing it in memory, because your 0666, when you look at it in memory, will be stored as 6606. Now, of course, if you load back from that 16-bit address, it won't be a problem, it won't get flipped or anything. If you're loading it as a 16-bit pair, it's only if you loaded it in as 2 separate bytes. And you can actually see we've done that here. Now what we've done next is we've actually used a label. Now I said before we can specify a label by putting some text at the left-hand side of the screen with no indent. And I always put a colon at the end, but you don't actually need to on this assembler. And then we've used a DB command, and we've specified to define 2 bytes. An FE in hexadecimal and a DC in hexadecimal. So it's 2 bytes here. And what we're going to do is we're going to use this address IAM a label as the source. So we're loading the value of the address IAM a label into HL, and the assembler will work out the value of IAM a label when the code actually runs on the processor. So the assembler is converting that for us. So HL now contains the address of that data that we've called IAM a label. What we're then doing here, you can see we've now got HL in brackets, and this says load the accumulator from the address in HL. We're then saying load the E register from the address in HL. We're then using a command incHL, which increments HL, adding 1 to it. And we then load D from the address in HL, and we incHL again. Now, why have we done this? Well, we wanted to load the 16-bit DE pair from the memory address in HL, but we can't do that in one command. The other thing is, because it's a little endian system, the low byte, the E register, has to be loaded first, and then the D byte, the high rate part of the 16-bit pair, needs to be loaded second. Well, let's see what actually happened there. Well, our value was FEDC, and we've loaded in to the accumulator E and D. So you can see the accumulator has been loaded in with FE here, and then our DE pair has been loaded with DCFE. And that's because, as I say, it's a little endian system, so the DC has ended up in the high part and the FE has ended up in the low part, because the little part came first, the low byte of the 16-bit pair. So that's what we've done there. Now, the HL pair is the most powerful of the 16-bit pairs for this kind of work. You can see here we can load the accumulator from the memory address in HL, but we can also load other registers from the memory address in HL. Other registers have similar functionality, but they can only work with the accumulator. For example, here we've loaded the accumulator with the value hexadecimal 69 and BC with the value C006. And then we've loaded the memory address in BC, specified by the brackets, with the value of the accumulator. So that has set the memory address in BC to the accumulator. Now, we can do that with the accumulator, but we couldn't do that with the E register. For example, if we did that, or the H register, that wouldn't work. We can only use the BC or DE pairs with the accumulator. It's only the HL pair which has the extra functionality. But if we look here, you can see that our 69 has indeed been stored back to that memory address as we specified here. So that's worked just fine. of course, we can do the same for writing 16-bit pairs. We just need to do them in 2 parts. So here we've loaded HL with the memory address C008 and DE with the test value 9876. We've loaded the low part into the memory address in HL, incremented, and then loaded the high part, again, little endian, so the low part E first. And then we can see that that has also happened. So we've loaded our DE with 9876 here, and this has been loaded in just here, which has become 7698 because of that little endian. Now, of course, we can only do this with 8-bit parts. We can't do load memory address HL with DE, that's an invalid command. DE cannot work with any register other than the accumulator, that is also invalid. Okay, so we've seen some memory loads there and we've seen some registers. Let's have a look again at that Incandec command. We've covered them briefly there, but I think we need to look at them a little bit more because they are really the most basic of the mathematical commands and we're going to need them an awful lot. So let's just take another look at them and just make sure we do properly understand them. So here we've loaded HL pair with the test value 00FE. We're going to show that to the screen and we're repeatedly going to increment it. Now this is a 16-bit pair and you can see our inc command is inc HL here, which means add 1 to 16-bit pair HL. That's exactly what we've done here. So we've got the value FE here, and if we just get our calculator up here and we type in the value here, FE, you will see that that is the value 254. Okay, so we've got our value FE here and we add 1 to it via that inc command and this will become FF. We then do another inc and of course 255 is the limit for an 8-bit single register, but we're using a 16-bit pair, so this is able to go over 255 and this wraps around into the high byte becoming 1 and the low byte becoming 0. So that 16-bit pair has allowed us to exceed the 255 limit, which is absolutely fine. And so our increments have created the correct values. Increment adds 1 each time. We also have decrement, which subtracts 1 each time, and that's exactly what we've continued to do. So we've gone from our 100, which is 256, subtracted 1 and ended up at FF, which is 255, subtracted 1 again, FE 254. There we go. Now these were incs and decs at the 16-bit level, so inc HL and dec HL, but we can also do these at the 8-bit level and we can inc H or L or any other of the 8-bit registers independently. So here we've inked L twice and we'll get a different result here, and this comes back to our negative numbers. So we started at 254 FE, we added 1 FF, we added 1 again and it's wrapped around to 0. As I say, minus 1 and 255 are effectively the same number because of this wraparound. So you can see that the bottom byte has become 0, but the top byte has become unchanged. Before, the top byte would wrap around and go up to 1, maintaining the 16-bit value, but now we're working at 8 bits, so the extra bit has been lost. So that's because we're doing inc L, not inc HL. And of course we can do the same with dec and we will get the same result. So we ended at 0, and if we do a dec we go below 0 and wrap around to FF, which as I say is minus 1, and FE, which is effectively minus 2. But again, just to make it very clear, because I misunderstood originally, the processor doesn't know whether FF is 255 or minus 1. It entirely depends how we use those numbers in our code, and we'll cover that in later lessons. So don't worry about it if you don't understand it at the moment. Now, all of these negative numbers are a little bit confusing, I know that, but we do have some things to help us out. And the one we're going to look at here is the Neg command. So we've loaded our register with the value of 1 here, the accumulator. Now, we can use the Neg command, and the Neg command only works on the accumulator, but we can use that to convert the accumulator from a positive number to a negative one. And so what we've done here is we've taken that 1 and negated it, and then negated it again and negated it again, and we'll see the results here. So here you can see we started with a value of 1 and negated it, and that has changed that to an FF, which is a 255. We then negated it again, and that flipped it back to a 1, and then we negated it again, and it became a 255 again. Well, let's just have a look at our calculator here, and let's see if we can understand that. So if we put a value of 1 in here, and then we just negate that, well, you can see that depending on the number of bits and we have, all of the bits will become 1, and that will become a value of FF, or in 16 bits, FFFF. And again, this is because we need enough bits to cause the wraparound of whatever register we will have. So if we were on a 64-bit system, we'd need an awful lot of Fs, and if we were on an 8-bit system, we only need 2 of them. So as I say, that's how the negative numbers work on these systems. It is confusing, I apologize, but that's just the way it is. But as I say, this is the first lesson. I'm going through a lot very quickly, but the intention is that you should go ahead and go and read the website, try these out for yourselves, and don't feel disheartened if you're feeling a bit confused, because the original tutorial series I learned from was called Learn Z80 in 28 Days. I cover that in about 7 lessons, so I go through this fast, and it's intended that you read it repeatedly and you try it out yourselves and you learn at your own pace. So hopefully that's what you'll do. Okay, so let's go for our last example, which is going to be some simple addition and subtraction. Okay, so we're going to do some mathematics now. Now on our Z80, the primary way of doing mathematics is always the accumulator. We can do some basic 16-bit mathematics using the HL register pair, which is sometimes called the 16-bit accumulator. I only heard it called that once, but it is a very good description of it, so I do like that description. Okay, so we've started off by loading some immediate values, loading A with the value F0, B with the value 2, and C with the value 10 here. And we're going to show those to the screen, and then we're going to do some mathematics. Okay, so our command here, add A comma B. As always, the source is on the right, the destination is on the left. So this says to add B to A, and that is what we've done. Well, A started out as F0 and B was 2. So this will effectively add 2 to the accumulator. But then we've got a second command here, which is add B. Now this doesn't specify a destination, which seems a little bit odd, but the thing to remember is the accumulator on the add command is always the destination. So we can save ourselves some typing and just not specify A as the destination. Add B, by definition, is adding to the accumulator. So this has effectively added B to the accumulator twice, and the accumulator has gone up from F0 to F4. So that's adding a register to the accumulator. We can, of course, add an immediate value to the register. Here we've added 1 to the accumulator, and this has changed from F4 to F5. We could, of course, if we wanted, use our standard hexadecimal representation with an AND, or our binary representation with a percentage if we preferred, but here we're just using an immediate. Of course, it would be worth noting here that add1 is the equivalent of inc_A, and inc_A would take a single byte in the resulting binary program, whereas add1 is 2 bytes. So that is a little bit inefficient there, but it's just an example. So here we've added registers and an immediate to the accumulator. Well, we can also do the same with subtraction. Here we're subtracting the C register, and then we're subtracting 1. Well, the C register is equal to hexadecimal 10, so this effectively changes our F5 to an E4, because we've effectively subtracted 10 via that C register, so that's changed the F5 to an E5, and then we've subtracted 1 via the immediate, which has changed the E5 to an E4. We can also do some basic mathematics with 16-bit registers, and that's what we've done here. We've loaded HL with 666 in hex, and BC with 1001 in hex, and we've added BC to HL, source on the right, destination on the left, and that's what we've done here. So our 666 here has become 1667 there as a result of that add command. So we can add a 16-bit pair to a 16-bit pair. We can't quite subtract a 16-bit pair from a 16-bit pair. There is no sub H, BC command. But there is a subtract with carry command. Now the carry we'll cover in a later lesson, but basically it's designed for overflow from a register. If we've overflowed a 16-bit pair, we can combine 2 16-bit pairs into a 32-bit pair, things like that. But we can use the SBC command to emulate a subcommand. All we need to do is clear the carry, and the OR command will have no other effect than clearing the carry. So this is effectively subtracting BC from HL. And so you can see we went from 666 to 1667, and then we've gone back to 666 here because of that subtraction. Now we can't subtract or add immediates in this way. We can only subtract or add pairs of registers. So we can't do add HL, 1, 2, 3, 4 or anything like that. We can only do that with 8-bit values. Finally, as well, the other way we can do subtraction if we need to is via the add command if we're working with a value here. So we can specify to load the BC register with a value of -100 in hexadecimal, and then we can add that negative value to HL. And as I said before, because the registers will wrap around, that will work just fine, and it will subtract that 100 from our 666. And that's what we've done there. And there we go. So that is actually everything we're going to be covering in today's lesson. Now, obviously, I know that I've gone through things very quickly here. As I say, the intention is you're going to go to my website and download the source code and have a go with it yourself, or at least have a look at the website and read through the text, because all of these examples are written in text there as well. And hopefully by reading it over again and trying it out, hopefully yourself, you will be able to get the grips of it, and hopefully that will help you out. Now, this is the first lesson in a series, so we're going to be going into a lot more later. I do want to tell you about some of my other tutorials which may help you out in different ways if this isn't what you want to see. Firstly, I have the Hello World series where I give a very basic Hello World example on all of the systems you may be interested in. Your CPC, your Spectrum, your MSX, your Sam Coupe, you name it, I've probably covered it. And I've got those series, and they also cover how to use an assembler on the command line if you don't want to use my build scripts. They also cover how to start up the emulator and things like that. If you've decided that Z80 looks interesting but you want to try something instead, I've also got 68,000, 6502, PDP-11, RISC-V, you name it, I've covered it. Again, lots of other tutorials on other kinds of assembly language, so please check those out. If you're interested and you're willing to put some money down, I would suggest you consider buying my book. If no other reason, it helps me out financially. It's called Learn Multi-Platform Assembly with Chibi Akamas. It's designed at beginners, but it's a very concise, straight to the point book. It covers Z80, 6502, 68,000, 886 and ARM. So a lot of content in there for your money. As I say, you don't need it. This tutorial series will cover everything I believe you need to know. But if it should help you out, and it will certainly help me out if you do buy the book. The other thing to tell you is, if this series hasn't quite worked out for you for some reason, but you do want to cover Z80, it might be worth you looking at my old series. It was done about 4 years ago. It's covering the same kind of content, it just does it in a slightly different way. So it was more interactive, where I was actually typing the programs out in the lessons, and I was using the WinApe assembler and debugger, which is all combined into one emulator. I still believe that is the best combination of assembler, debugger and emulator, but I know a lot of people aren't interested in the Amstrad CPC and have trouble getting it working on Linux and things like that. So that's why I'm not using it anymore. But if that might be the solution if you haven't found out this to be the format that you prefer. Anyway, I hope you've enjoyed this today. If you have, like and subscribe, because there's more coming, and hopefully I can help you have some fun with your assembly language. Thanks for watching today, and goodbye.